Before we get started, I'm just going to make some important announcements. So the first one being that we informed the teachers about the RBC mentor session a couple of weeks ago because there hasn't been too many traction yet, and that may be because students are preparing for their exams, and it's almost the holiday season. So we have decided to postpone the workshop to a later date, and we'll have the details out for you once we know. So that RBC optional workshop with mentors has been postponed. The second thing is that this binary exploitation is our final CTF workshop for this year. Our next week is going to be a workshop on intro to critical thinking with SANS Institute. It's not going to be a hands-on CTF workshop. It's going to be a different style. It's going to be great. There's going to be a lot to learn. So please make sure to join that workshop, and it will be happening the same time, Wednesday from 5 to 6 p.m. It will be an hour long. And then that will be the final workshop for the year. And this is the final CTF workshop for this year. For the 2021 schedule, we will be posting that up sometime around next week, end of next week. And once that schedule is up, we will let the teachers know. We will send you an email and also be updated on the CanHack website. And also, as always, that all of our recordings are posted online to the CanHack Hub. For the reverse engineering workshop, we had some difficulties and we weren't able to record that. So I will be re-recording that session. And then hopefully that will be up next week along with binary exploitation workshop. So then you will have all of the workshops that we've done so far in the CanHack Resource Hub, and you can, throughout the holidays, you feel free to review them, because for the second semester, we will be jumping into the 201 topics. The 201 are going to build on the topics that we discussed in 101, so they are going to be much harder. They're not going to, we're not going to go over the same stuff again. So it's important that you watch all of those workshops before. We have our TA today. Our mentor TA is going to be Albert. And at any time, if you have any questions, please feel free to send them in the chat box, and Albert will help you out. And then if you're experiencing any technical difficulties, Madison is here to help with any technical issues. Please feel free to ask questions at any time. In the chat box is open to everyone. You could send it privately to all panelists, or you could send it to everyone. It's probably better to share the questions with everyone if you're comfortable, because other people might have the same question. And so let's get started with binary exploitation. Before we start, I just want to mention that this is probably one of the most challenging topics for CTFs, as was reverse engineering last week. So with this topic, it requires a lot of understanding, and even for myself and Albert, we found the challenges to be quite challenging. So it requires a lot of, critical thinking. It requires a lot of sometimes research and Googling, like the answer might not be obvious right away, and requires a lot of trial and error. It's just important that while you're doing these challenges that you don't give up. And, with practice, you will get it. So if you find the concepts hard, don't get discouraged, because these are difficult concepts, but, with practice and hopefully with doing them a couple times and with really understanding what's going on, you will get them. So let's get started. So what is binary exploitation? Binary exploitation involves taking advantage of a bug or vulnerability in order to cause unintended or unanticipated behavior in the problem. Usually when programs are written, there's going to be some sort of vulnerability that you can exploit. And with binary exploitations, it's often due to memory corruption. Some attacks on memory corruption are like buffer overflow attacks, which I'm sure some of you might be familiar with. So again, so binary exploitation has to do with memory corruption. Usually in CTF challenges, it's usually memory corruption problems, buffer overflows, have to do with heap overflows, format string errors, and we're going to be talking about some of that today, and then in some of that in the next year. Okay, so most importantly, when we're dealing with binary exploitation, we are dealing with looking at programs. And it's really important to be able to know how to run a program file. So we're just going to go over that basic before we start so that everyone knows how to exactly run the program file. To run a program file, all you have to do is append a / before the name of the program to run. So you're going to do / and then the name of your program, and that command in the command line will run the program named run. So let's just do a practice challenge right here. It's called practice run. And today I'm going to be using the shell server because just to show you guys that you can do all of these problems within the shell server. Okay, I'm just going to clear this view so we can have a nice clear view. And I'm going to cd into the path that they've given us. And I'm going to list out what's in this path. So we have a program called run this. It's highlighted in yellow, which tells us that it's, a program. We can also see what type of file it is because we don't see an extension. We can also see what type of file it is by using the file command that we introduced in the forensics workshop. So we could do file, run this. And it's telling us that it is an ELF, 32-bit LSB shared object. When you see ELF, that is an executable Linux file, which means that it's a program. So now we know that we have to run this program. To run this program, we're going to add / run _ this, which is the name of the program. And when we hit enter, it should run the program for us. And running the program is giving us the flag. So that is our first flag. That's how you get it, and that is how you run programs. So most of you have done binary exploitation challenges according to the poll, and a few of you haven't, which is okay because it's going to be an introduction to them, but it's good to know that most of you have had some sort of introduction to them. So we're going to build on that. And for some of you, these problems might be very simple because you've done these challenges before. Okay. So because these problems have to do with memory, it's really important to understand how memory works. So we're going to discuss CPU, register, stack, and memory again, and we also discuss it in reverse engineering, but this is good for those of you who weren't in reverse engineering. You can get a little bit of an idea of what we discussed in that workshop. So let's talk about memory. So many of us know that our computer cannot function without the CPU. The CPU is where all the magic happens. It's called the central processing unit. The CPU comprises of three things: the arithmetic logic unit, the ALU, and the ALU consists of two things: the arithmetic unit, which is responsible for mathematical functions like addition, subtraction, division, multiplication, and logic unit, which is responsible for logical operations like XOR, AND, NAND, or logical functions. And the control unit, which is the second component of the CPU, it controls and directs the main memory, and it's responsible for instructions that are sent to the CPU. And then we have the registers, which are going to be very important because that is where the corruption happens. And the registers are small, high-speed CPU storage locations where data can be efficiently read or manipulated, and you can hold data temporarily. When you have a program, it needs somewhere to store the data, and that data is usually being stored in the registers in the stack. So let's take a look at registers and what exactly registers do in detail. So registers hold temporary data that is needed by the CPU to execute instructions. They perform operations and they store resulting data. And we took a good look in reverse engineering of how exactly that process takes place, how the stack is set up, how registers use push and pop instructions. So basically, they're responsible for executing any instructions that the CPU has. Right now, if I were to type something, it would be stored in the register, that data that I'm typing, and then the CPU would execute it using a mathematical or logical operation. So now registers, we know, only hold small amounts of data. In a 64-bit architecture, the CPUs hold 64 bits of data per register, and in a 32-bit architecture, it only holds 32 bits of data per register. It's important to note that what is the CPU architecture? What does that mean when I'm saying that? The CPU architecture determines the design of the processor, the instructions that are supported, size of registers, and other factors, and that's important to note to understand what type of architecture you're working with during a capture the flag challenge. And most of the time, it's going to be x86, either 32-bit or 64-bit, which is one of the most common architectures for CPUs. And it was developed by Intel back in the day. One important thing to note is the instructions that are supported based on a CPU architecture. That is talking about the assembly language. So if you're ever working with directly assembly language, it's really important to know what type of architecture you're working with so that you can properly read those instructions. So here is a look at what some of the registers look like. These are the general registers right here, general purpose registers, and then we have the stack pointer and the base pointer. And the stack pointer, base pointer, oops, my mouse is very sensitive. The stack pointer and base pointer and the instruction pointer are going to be very important, and you're going to see in a second why they're super important. So these registers, they're general purpose, and for this topic, we're not too worried about EAX, EBX, ECX. What we are concerned about is the stack pointer and the base pointer. The base pointer is also known as the frame pointer. It contains the base address of the function's frame. And when we were setting up the stack last time, you saw that the EVP was what was always at the bottom. We always had to start with the EVP. We had to take the old EVP and move it into the ESP and then set up the stack that way, because the ESP, the stack pointer, is the current position of data or address within the program of the stack. So the ESP is always moving to where the data is, and the EVP stays right at the base of the function. So we'll see that in a little bit in this program right here in the stack. So what is a stack? Stack is a reserved area of the memory used to store temporary data variables created by each function, including the main function. The main function is also, known as the program. It's what the program does. All x86 architectures use a stack as a temporary storage area in RAM that allows the processor to quickly store and retrieve data in memory. So anytime you're running a program, anytime I'm using my keyboard to type, it's getting stored in the RAM in what's known as the stack. Higher memory addresses are at the top of the stack, and we discussed there was a lot of confusion last time because these memory addresses will usually be in hexadecimal. So it's really important to be familiar with hex. Not so much that you can, easily convert it, but just that you can understand that when you see a value that this is a hex value, or this is a binary value, this is an ASCII character, or this is a decimal value. And if you want to familiarize yourself with those concepts, please feel free to look at the forensics workshop, because we covered those things in detail in that workshop. So as we were saying, the higher memory addresses are at the top of the stack and the lower memory addresses are at the bottom of the stack. The stack follows a LIFO method. It's called last in, first out. So items that are pushed on top of the stack last are popped first. And we can look at the stack like a bunch of plates being stacked on another. So here is the bottom, and you're putting more plates on, which is the instructions, right? And so obviously you cannot remove a plate in the middle if there's a plate on the top. To remove the plate from the middle, you have to first remove what's on top sequentially. So that you can kind of think of a stack like that. So whatever goes in first is probably going to come out last. Whatever goes in last is going to come out first, but whatever's gone on first, it will be at the bottom. So those things after it will have to be popped off first. Data is stored in these registers, in these stack places, using the little endian method. We talked about that before. So this is this is just a pretend hexadecimal value. Hexadecimal 1, 2, 3, 4, 5, 6, 7, 8. And little endian method takes the least significant bit and first, and then to the most significant bit. And if you remember from our forensics workshop, the least significant bit is the rightmost bit, and the most significant bit is the leftmost bit, because the least significant bit has probably the lower value. It's 16 raised to the power of 0, 16 raised to the power of 1 in hex, which is why it's known as the least significant bit. So when you're entering it into the stack, it would be following the little endian method. So it would be 7, 8, 5, 6, 3, 4, and 1, 2. So just remember that, because when you are deconstructing that and you have to figure out what the actual, when you're taking that information out and trying to figure out what the hex address is, when you see this, you have to remember that it would be the opposite. So it would be 12, 34, 5, 6, 7, 8 as the actual hexadecimal address. So in 32-bit registers, memory addresses of registers are 4 bytes apart. So let's see right here, right over here. This is the base. This is the EBP. This is our base pointer. So all our stack is going to be built above it. This is where the function parameters will go, or the data that needs to be stored was going to come on top of this. Local variables that are part of the program are going to go below this, and we're going to make room for them below the base pointer. And this stack pointer moves, this stack pointer moves accordingly. So let's say before we had any local variables right here, our stack pointer would have been right here. But as we add more local variables, our stack pointer changes. If we only had up to here, this is where our stack pointer would be. Our base pointer always stays here, which allows us to talk about the other functions relative to the base pointer. And if you remember from last time, this was EBP plus 4, which always stores our return address value. Above EBP plus 4 was EBP plus 8, EBP plus C, aka EBP plus 12. Remember, these values will always be stored in hex, so 12 will be represented by C. So they increment by 4 bytes. So it's important to remember that. And this is going to be our base pointer. So now let's talk about buffer overflows. So what are buffer overflows? We've just taken a look at the memory right now. Buffer overflows are a violation of memory security because you're doing something to memory to corrupt it, to exploit it. A buffer is a specific area of memory that an application has access to hold temporary data. That buffer, that buffer is usually in the stack, and most of the times when we're doing buffer overflows, we're going to be using the stack. There's also another area of memory called the heap. We're going to be covering that in binary exploitation 201. So for now, we're just focused on the stack. So everything we just talked about a couple of seconds ago, just keep that in mind. Imagine that stack. So the buffer is a specific area of memory that an application has access to, and usually within the stack. So when an application receives more input than it expects, a buffer overflow occurs. Now, why would that happen is because your program probably expects a certain value or certain number of characters that it's expecting. If you give it more characters than it was expecting, and if there's no bounds checking in place, meaning the program is not checking to see if it matches if the quantity of input matches what it's expecting, and if it doesn't check that, then that extra characters will overflow into adjacent memory locations, and that is going to cause a buffer overflow. So basically, they allow access to memory locations beyond the application's buffer, resulting in the program crashing. This enables an attacker to inject their malicious code into this area of memory. Because let's look at a simple program right here. So this program takes your password, and most passwords, or we're told to think that passwords that are 8 characters long are secure, which is far from the truth. But let's say this is a very outdated program and it's expecting 8 character long passwords. So we have, our password, but our password is not 8 characters long because we're trying to make it a little bit more secure. So we've made it 10 characters long. So we're going to put our password 1, 2. There's no bounds checking in place in the program. So our password leaks into other areas of memory, which are not being held for the program. So this was the buffer initially that we had for holding the input, but now it's leaked into other areas of memory. So let's go back and look at the stack. So right now, let's say this is going to be our, first function parameter or first value that we're going to put. So let's say that our password, it only expects 8 characters. So when we put it in here, it's going to overflow into here, which is the return address. So is that dangerous? Yes, that is. It's coming up into the return address. Now, as we know, the instruction pointer, which is, right over here, it points to the next address of instruction pointer, or the return address points to the next value of where the instructions should be executed. So if it's overflowing into here and an attacker understands how to manipulate the binary so that the computer cannot just take that as 1, 2, take that as an instruction, then we can cause this to execute a malicious code from the attacker. So that's why buffer overflows are very dangerous. So as I just mentioned, if an attacker understands how memory and binary works, then they can craft a code that can be interpreted by the computer and executed. If it overflows into an instruction, then the computer is going to begin executing it, which is very dangerous because then an attacker with malicious intent can get the program to do whatever they want. They can overwrite the return address to go to where they've placed the malicious code in the memory, and the malicious code in the memory can be a denial of service attack, which crashes the server. Just as an example, and buffer overflows are one of the most common types of attacks. They're in the OWASP top 10 attacks, so they're very, very common. If you were to Google buffer overflow attacks, you would see a lot of buffer overflow attacks or vulnerabilities that were exploited in hacks, data breaches, and all sorts of things in 2020. So it continues to remain one of the most, one of the biggest vulnerabilities that we face in the cybersecurity industry. And so it's really important that we, take measures to mitigate these vulnerabilities. So the problem with why buffer overflows happen is because of the way that programs are written. Many of the programs are written in C or C++, which is a language known to be susceptible to these type of attacks because it doesn't do bounds checking. So it lacks built-in protection against accessing data anywhere in memory space. If you're able to manipulate it, it will allow you to access data anywhere in memory, which is dangerous because it allows an attacker to play with our stack, which is dangerous. And it doesn't automatically check whether inputted data is within bounds or, within the characters that is specified by the program. So here are some dangerous C functions. When you're looking at a program and you come across one of these functions, most likely that program will have a buffer overflow vulnerability, or it will be susceptible to a buffer overflow attack. So just keep these functions in mind. Most of the time you'll see this string copy, gets, fgets, printf, which are very common and which are have a lot of vulnerabilities. This gets, fgets, and gets, it's a horrible function. It should not be used. And it tells you that in the manual of this function that don't use this function. It's very dangerous. So now let's actually take a look at a buffer overflow challenge from the CTF, from the Pico CTF platform. So this is overflow 0. Now it's really important that you have a little bit of a knowledge of how to read programs, especially for buffer overflows, usually C. But even if you don't have that knowledge, just by looking at the program, it's pretty simple to deduce what's actually taking place. So let's start off here. at our main function where everything takes place. So let's start off at our main function. What happens is this file, this function right here, is trying to open up the text file. And if it can't open the file, it's going to get this error right here, because you don't have the privileges to look at that. Then it's going to read the file right here, and it's going to set up a signal, seg faults, and it's going to set up a signal. And if it gets a seg fault, which is program crashes, it's going to run the seg handler, which is this function right here. It's going to give us, it's going to give shell privileges. So it's going to give us the ID that we need to be able to view, to cat the file. And if argument is greater than 1, it will pass that argument to the vulnerable function right here. The vulnerable function needs an argument. It takes an input of 128 characters, which is specified right here. It uses this vulnerable dangerous function that we talked about in the old slide. So we probably will have a buffer overflow vulnerability, and it takes that and it puts it into the buffer. If this is the input that this is the characters we're expecting, and so this function str string copy, it doesn't do bounds checking. It will take whatever input you give it and it's going to put it into the buffer. It doesn't care. It doesn't do any bounds checking here. There's nothing in the program that shows that it does. So if that happens, we're going to cause a segmentation fault. And if a segmentation fault, which is a program crash, occurs, that it will run the seg handler, which will give us the flag. So that's basically what this program is doing. So now let's take a look at the program right here, overflow 0. So let's copy this location. I think this needs to be refreshed. So let's refresh our web shell. Okay, perfect. So I'm just going to give it my username and my password. So let me just clear the terminal so it's easy for us to see. We'll screen that. And we're going to cd into our location that we just copied. Let's see what's at this location. We have our flag.txt, our vulnerable program, and the source code. So let's try reading the flag and see if, so we don't have the permissions to read it. So let's do this, which will tell us who has permissions. So we only have permissions to see the source file. We are Hacksports, the group, but we don't have permission to see the vulnerability or the flag text. This is the group ID that has the permission. So what we're going to do is we're going to try, and if you hadn't already seen the source code like I showed you before, you could cat the source code right here and take a look at that. So this is the same function that I just showed you in the slide. So we're going to exit out of this function by doing Control Z. Let's clear the terminal again so we have a nice clean slate. So let's run the program by appending the // and it says please enter an argument next time. So we can see, we can test it by giving it characters. So we know that it was expecting 128 characters. So let's just give it, I don't know, let's just give it a bunch of A's. So it's giving us what we entered so that we did not crash the program, because obviously our buffer size, these are not more than 120 A's. Well, let's give it a whole bunch of A's and let's see what happens. Let's see if we can crash this program. By giving it all of these A's, we are overwriting it into adjacent memory locations. So I'm just giving it a whole bunch of A's, hoping that, let's get more than 128 A's, a lot of A's. That looks like a lot of A's, right? So let's hit enter. And we crashed the program, which, caused the seg handler to print out the flag for us. So that was easy. We were able to crash the program. So there you go. There's our flag right over here. So all we had to do was give it more input than it expected. it expected to get a 128, and we gave it more than 128 characters, and it probably leaked into other areas of the memory, which caused to run the sig-sagif handler, and that caused to read the flag. So now let's look at that. So that was it. No program is going to actually function like that, where we give it a, where it will read out a file if the program crashes, or read out like a password file. I don't know, some programs might, but in reality, most programs will not function like that. So let's add more usability to it from a hacking perspective. Let's give it what's known as shellcode. Shellcode is a small piece of code uses payload in the exploitation of a software vulnerability. This is an example of a shellcode. To us, it doesn't make any sense. These X's are hexadecimal values, but to the computer, this represents instructions. So this is telling the computer to do something, and this is example of a shellcode. This is going to open the bin/sh, which is, it's going to open up a new shell, which is going to allow the attacker to execute commands in the shell. So the shellcode is going to be pure hexadecimal values, and the shellcode cannot contain null bytes, which are just zeros. It's a string delimiter in string, so it's going to stop processing if it sees that. So you have to make sure you don't have any null bytes in your shellcode. There are other instructions. You can find shellcode on shellstorm.org. So you could just Google. So if you know what the structure of your program and the architecture you're looking for, you can just look up the shellcode. You don't have to write the shellcode yourself. That would be very challenging. You could just look up pre-existing shellcode. So this shellcode allows, shellcode allows attackers to inject a shell so that they can execute commands, which is why it's called shellcode. So let's look at the handy shellcode problem from the Pico CTF. So what is exactly happening? So we have a vulnerable function which runs gets. Again, we talked about gets in the dangerous C functions. Gets is a dangerous C function, so we know that there might be a buffer overflow vulnerability. So it runs gets and displays onto the screen with puts, and puts passes the argument buff. So let's look at what buff is. So right here, the buff that is defined is 148. So it's right here, it puts whatever we put into buff. Right here, the buff size is 148 characters. And we can put our shellcode into here and it will execute that. And here's the function pointer to execute that code. So basically what this program is doing is we are going to give it shellcode and it's going to run the shellcode for us. So what I'm going to try to do, because I know it's going to use shellcode, I'm going to try to copy this shellcode so that I can use it. And let's go into our challenge. So this is our handy shellcode challenge. Looks like I'm going to have to copy that again. So let me just show you how I got that shellcode. Shellcode, Linux, x86. And the shellcode that I'm using, as far as I can remember, is this one right here. I copied it right from here. And when you're, you might have to experiment because I did use other shellcodes, but this is the shellcode that actually worked for me. For this program. And then when you're copying and pasting, you have to make sure it's all in the same line. So that's where I got the shellcode from. So let's go back and do this problem. Okay, every time it asks me to put my username, which is kind of annoying, but it times out. Okay, I put my password wrong, I could tell. That's what you get for having a super long, complex password, but hopefully I put that properly. Nope, I did not. I'm gonna go slower this time. There we go. Let's clear that. So we have a nice clear screen, and let's cd into what I pasted. And here is our vulnerable function. So let's run the vulnerable function. because what we did, and it's going to ask us to give some shellcode. So now let's copy and paste our shellcode from here. Copy, and let's put that into right here, and let's see what happens. Okay, so it had a segmentation fault, it crashed, it almost gave us a shell, but it didn't. We need to have a shell that we could sustain. So let's try it again. Let's try to feed it the shell by writing a simple Python program. We have to make sure we put the quotes around it so that it does not treat it as a string, it gets treated as bytes, because when we just inputted it into that area, it was not taking it as bytes. And so you do need to have some you know, Python, some scripting knowledge to do this. So let's put it into Vuln and see what happens. Okay, so I have not entered that correctly, and it almost executed, but it's not holding the shell for us. Let's see if we can go back into this. See if we can go back and run that again. We can use a trick called cat, and let's put parentheses around our program. Oh, that is bad. I have not been using Python. I thought I was putting Python there. So this is a Python. This is a Python program. We're going to feed it a command line input. We're going to ask it to print the shell code. We're going to get that to go through cat to sustain a shell, because without doing that, it would not sustain the shell for us. And we're going to pipe it into the program. That's how we're going to feed the shell code into our program so that we can sustain a shell. Let's hit enter. Okay, so our shell code is here. So now we could see the different files. Let's try printing the text, the flag text file. And there is our flag right there. So let's go through that problem one more time. Let's exit out of the problem. Let's go through that problem one more time, just to make it clear what exactly happens. So we ran the vulnerability program. It asked us for the shell. This is our shell code, but it gave us the shell code back, means it was not actually executing that as shell code. It was taking that as a string. So to solve that problem, we could write a Python program and feed it into there. So, and we have to make sure we put quotes around that. The shell is looking a little bit funky. That's okay. Okay, I don't know what I did. So let's just do that again. Do you guys see that? It's a little bit buggy. So let's just put that right here, that quote. Okay, I have no idea why that is not working, but so basically, okay, there we go. Let's clear that again. The shell is being a little bit buggy. Let's write the program again. Paste our shell code. Oh boy. Okay, I have no idea. Okay, so let's just copy and paste it from here, because the shell is really being buggy with me right now. So let's just copy the command, because I have it right here, and paste it into that, and let's talk through it again. Paste. Okay. So it gave us the shell code because we printed the shell code like that, and we put it all through cat, because cat is it takes a standard input and it gives us puts out whatever we give it into an input. So to keep a consistent shell going on, to make sure that the shell stays there, we used cat. We piped it through the vulnerable program, all of that shell code, and it gives us a shell code right here. We can type commands. We can type whatever commands we want. It allows us to print cat flag.txt, and there's our flag. And there's some crazy stuff happening with the shell, so I'm going to reset the shell. So that's one challenge with using this shell, is sometimes it can be buggy, the shell server. So if you want, you can obviously SSH into the shell from your own Linux machine to make things easier. We'll just come back to this later, and let's talk about what the solution was. Okay, so the solution was that we are going to inject the shell code. The program needs to hold the shell and interpret the shell code as bytes and not a string. And the below Python program will allow us to achieve that. And this was the program. We use a Python program to print this shell code into a vulnerable. We piped everything in here, but we also wanted to maintain our shell. And we did that by using cat. So basically that held a shell for us, and it allows us to get the shell and to cat our flag.txt file. I will share alternative ways that you could solve this. You can use pwntools, which is a CTF framework and exploit development library. You can craft a script, and somebody asked if you can only use Python programs or you can use other. Yeah, if you know how to craft a script in another language, you can use any language to do that. There's multiple ways to solve this problem. If you're familiar with the Metasploit framework, you can use Metasploit to solve this problem by injecting a shell code. You're going to have to make a remote connection then to the server. That the way I solved it, you can do it without, SSHing or anything, because it allows you to create that within the server, within the Pico CTF server. So pwntools makes exploit writing a lot easier, and you could check it out. When the slides are up, you can go to these links. So to solve this with that, this would have been the command. You would have imported this, and luckily the Pico CTF comes installed with pwntools. So if you want to use it to make your life easier, then and if you understand the syntax of it, by all means. So what this would do is it's going to print the same thing that we were doing, but it's going to print the assembly length. This means assembly, and this is the shell code right here, and it's pwn shellcraft Linux. That's the shell code line, and of course we close that, and it's the same thing. We catted it to keep a consistent shell, and we piped it through the program, and that is one way to solve it. Another way is a script. I've linked a script you can use that I found on GitHub right over here. That works as well. So that was shellcode that allowed us to see that, there's other applications besides just crashing the program. There's other things you can do with buffer overflows exploits. Let's actually look at a diagram of what a buffer overflow, how it can be really, exploited. So right now we have this is our stack, and we talked about our stack. We have our EBPs probably over here, our ESP is over here, our return address is here, and this is our buffer right over here. And as you could see, it's expecting 12 characters. That's the buffer size for this. So let's say this is a password program. So you enter this hello, and that's fine. It's within bounds, so there's no problems right here. But let's say that you have you overwrite this program, and it only allows you a space of 12, but you overwrite it by, let's say you put way more characters. So let's say you've overwrite it with, this is your code represented by A's, and right over here, you've been sneaky, sorry about that. You've been sneaky and you've put in a hexadecimal value address. So this is also known as return address. Return address tells us where the next instruction to be executed is. So in this return address, you've put the hexadecimal value of where you want the pointer to go. So when it sees this, it's going to end up going right over here. And this is where our malicious code is going to be. This is where a hacker can put their malicious code. Now, the address here is 80 C03508. So does anybody remember why in this area it's represented backwards? Why is this address 0835 C080? Does anyone remember why it's represented like that? Yeah, exactly. It's because of the little endian method. So exactly, because of the little endian method, this hexadecimal address is located. It's written in little endian, but it's going to take us right here. And right over here, the attacker is going to put their malicious code, and what it's going to happen is it's going to go through all of here, but when it gets here, it's going to have the return address overwritten. It's going to jump to this location right here and execute the malicious code, whatever code that is. It could be shell code, it could be anything. And that's what's going to happen. So this is where it's really dangerous. But the tricky part is how exactly would how exactly would you figure out where, where to put this? Like, you have to know exactly where the return address or the return pointer is located to be able to put this address into that location. So there's a neat little trick that attackers use, and it's called the NOP sled. The NOP sled or no op sled means no operation. Wherever the computer sees no operation, it's not going to execute anything there. It's going to slide by wherever it sees the no operation. And that's why it's called sled, because it literally slides through. So no op means no operation. And it's used because it's hard to find the exact location in memory. So one thing to do is just to overwrite it and to use an op sled. So many Intel processors use hexadecimal value 90 as in no operation command. So when the CPU sees the hexadecimal 90, it knows not to do anything. So it just slides right through. A string of hexadecimal 90 together is known as a NOP sled because it's a bunch of 90s. It's just going to slide through. So attackers abuse this NOP by inputting a NOP sled followed by a malicious code. So what they do is because they don't want to exactly figure out where stuff is located, they're just going to put a bunch of hexadecimal 90s or whatever is represented by the processor as no operation. And the program is just going to not do anything. And then when it gets to the end of the NOP sled, it executes whatever code is there. So the CPU ignores the NOP sled until it gets to the last one and executes the code in the next instructions. So if I have a bunch of 90s, it just doesn't matter where it is in memory. It's just not going to execute. It's just going to slide through. And wherever it stops, and you've put your malicious code, that's what it's going to execute. So this is a little trick to bypass that, to bypass knowing exactly where something is located in a memory. So let's look at slippery shellcode, which is a problem that kind of has to do with NOP sleds. Now, a lot of times in the Pico CTF challenges, I found that the names of the programs, they really kind of give away like what you're supposed to do, because this says slippery shellcode, I kind of had an idea like slippery sliding, like it might have something to do with the no-op. So let's take a look. So what is happening exactly in this program is we're going to input the shellcode, asks us to put the shellcode, and it's going to execute the vulnerable function. The vulnerable function is going to put the shellcode into the buffer and give that to us. The buffer is going to get executed with the function pointer and with an with an offset added. So we need a way that doesn't matter where it lands. So because of this offset value, it would make it very tricky, and we'd have to know like, where is it offsetting? Where can we overwrite the return address? Where should we put our code? We'd have to exactly figure out where in memory that's taking place. And so we need a way that it doesn't matter where it lands. So we're going to use the no operation sled. So let's take a look at this problem. Again, I'm just going to copy the shell code from before. I'll come back and copy that because I'm going to have to go into here, into the shell. And let's just refresh this. Let's refresh this and come back to it. Okay, let's clear the terminal so that we have a nice clean view. And let's get into this slippery shell code right over here. And let's copy the path. And let's paste the path right over here. Hopefully the shell will be kind to me this time and not malfunction. So here we have the vulnerable function, and we can cat that to read it. This is the same function that was shared on the slide. You feel free to follow along if you haven't already done these challenges on the Pico CTF platform. So let's just clear our terminal and let's run the function. Let's see if it is going to allow me to just enter my shell code. That's right, I still have to copy and paste my shell code. So let's see. What do you guys think will happen though if I input the shell code? Does anyone have an idea what's going to happen if I just input this shell code like that? Does anybody know? Okay, let's see if an error occurs. Yep, so it needs, yep, correct. So it's reading it as a string, it's outputting it back to me, and also an error is occurring, a segmentation fault, so it's just not working out. So we might need to use a Python program, correct. So let's start off with our Python program. And again, our code will be very similar to last time. We have to sustain a shell in the we have to sustain a shell. So let's kind of make it very similar to what we did last time. Try doing these NOPs. Let's use a NOP, right? We're going to use a NOP sled, and let's multiply that by, I don't know, let's look at what the program said. The programs had an offset of 256. Okay, so let's override that offset so we can just slide through it and not worry about what's going to happen. And then let's add our shell code right over here. Let's cat that. And let's pipe that through the vulnerable function. So you have to be very careful when you're writing a program, because one small error can cause your entire program to not work, which is really frustrating. I feel like, I hope I'm doing everything right. If you see any errors, then let me know. Even right here, the spacing, which might cause it to not work properly. So let's just fix that. So this is the shell code, same shell code as before. And I showed you guys how to get the shell code, right? So let's just, okay, so that seems to work. So let's just see if it's allowing us to execute commands. So it's not. So that means there's something wrong with the program. Oh yes, correct. There is an error in my program. Yes, it does. So that's so funny, because I was just talking to you guys about how you should be careful when writing your program. And I did exactly that, is I did not made a silly mistake. So let's fix that. That is correct, because we need to interpret this as an entire command. So it should be before the print function. Okay, so let's see. I think it should work now that we've fixed our mistakes. Perfect. Thank you, guys. You are Python experts. cat flag.txt, and there we go. So that wasn't too bad, right? All we had to do was, again, this was very similar to the previous shellcode problem. The only difference is now we're adding a no-op sled, which is bypassing that offset so that we don't have to sit there and worry about where exactly in memory something is taking place. So that allowed us to slide through that offset, ignored it completely. But when it came to the end of 256 no-op operation values, it executed the shellcode. And it gave us a shell, and we were able to read the flag. So this was the only addition was that we needed to, bypass that offset. So let's go back and let's take a look at the solution. So we have to write a program to print out no-op, so it overrides the offset and executes the shellcode. And that program is right over here. This Python, this is the what we want to print in these quotations. This is the no-op, and it's going to be a no-op sled because we're going to print this 256 times. We're going to add our shellcode at the end of it. To sustain a shell, we have to, put it through cat, and then we're going to pipe all of that. That's why it's in parentheses, because to make sure that it is interpreted as a whole, and we're going to pipe that all through the vulnerable program, allowing us to get our shellcode. And like you saw, like a small error, like I made, like a small error like that with the double quotes, like it will set you off and you might get frustrated. So make sure that you are, checking your Python code or whatever you're writing, like make sure you're checking your commands, because sometimes it just might be like a small error in your command, the way that you're writing your command, that's causing it to not work. Okay, so I'm going to talk about a very helpful program called GDB, which is also known as a GNU debugger. How many of you guys have used GDB before? Just curious to see if anyone has used it before. There's no poll for this. You could just type, let me know in the chat box. Okay. Okay, so some of you have used it. That's awesome. So basically, it allows you to see what's going on inside another program while it executes. So we could have gone into any program, and while the program is running, we can start our GDB and see what's happening with the program. It's going to allow us to see, it gives us a good idea what's happening with the memory as well. We can set breakpoints, we can see the functions that are being called and the exact locations of those functions. So GDB is a very, very helpful program when you're debugging or trying to find vulnerabilities, exploits, especially very helpful when you're trying to you do buffer overflows, because it tells you where in location, where in memory something is, and using that you can try to craft your code that you're crafting. So a lot of you haven't used it. That's no problem at all because it's very, very similar. It's not very similar. I'm not sure if it's similar to Visual Studio. Has anyone used Visual Studio and GDB, and can they comment on that? Like, is it similar to that? I'm not sure. But let me, so this is the source if you want to download that. So PicoCTF already comes with that installed, so we don't have to worry about it. We can use that within the shell. So if you're trying to solve, the way I'm solving all of these challenges is assuming that you only have access to the PicoCTF shell, so you can do all of these things within the shell without having to install anything that's not already installed on there. So GDB can do 4 main kinds of things. It could start your program, specifying anything that might affect its behavior. So you could start your program at a breakpoint. You can make your program stop on specified conditions. You can examine what happened when your program has stopped, see where the frame pointer, the stack pointer, the next instruction pointer is to see what you might have to override and manipulate. You can change things in your programs. You can experiment with correcting the effects of one bug in another. Okay, so to the Visual Studio comment, Visual Studio does have a debugger. So if you use Visual Studio, then maybe that it has a debugger, which might be very similar. So use whatever you're comfortable using. GDB is great because it's command line, and we can use it within the Pico CTF shell. But if there's any external tools that you use that you're more comfortable with, you can use those as well. So let's look at GDB commands. This right here is a really great program. It has a modular interface, which looks like this. So it's a little bit different than the command line interface. And I've linked all of these. These are the basic commands for GDB. To start it, you start GDB and you put the program after that. And this is to quit. The full syntax of the various commands can be found at this link at the documentation. You can find that on the main GDP source code page. So why did I mention GDP? We're going to see in a second when we solve overflow 1. This is similar to overflow 0. The name tells us it's going to be like a buffer overflow exploit. So let's take a look at what's going to happen. So there's a function that's called flag. Where is the flag function? Yep, right here. And it's going to print out the flag.txt. And the vulnerable function is running gets again right here, which we know that this program has a lot of vulnerabilities. We're using printf, which can have a format string vulnerability. We're using gets. So there's a few ways it could be exploited, but we're focused with how to get our flag. So basically, the vulnerable function is running gets. Then we have our this to set up our buffer. Our privileges get raised so that we can read the cat file when the program runs, and then the vulnerable function gets run, which will show us the address that it's run to. So when you run the vulnerable function, we're going to get the message. We're jumping to this, and that's going to show us exactly which hexadecimal value we're located at. So let's take a look at this program. Again, I feel like I will have to refresh my shell if I want it to be kind to me. So let me refresh my shell and log in. Also, if you are following along, please feel free to follow along because sometimes we learn better when we are doing things. Okay, so clear the terminal. Let me copy and paste what is that problem. It's overflow. Okay, so you can cat the vulnerable.c file, the source file, to see what's happening, but let's run the program and see what's going on. Give me a string and see what happens. Okay, so I gave it a random string and it tells us we're jumping to this location right here. Now, can anybody just as a, not that it's related, but I'm just curious, can anyone tell me how this address would be represented in the stack? If let's say we were to look at the stack right now, how would this address look like in the stack? Can anyone tell me what it would look like? Any guesses of what that would look like? Yeah, yeah, we're gonna have our base pointer. Yep, so it's gonna be like 05870408, correct? So it's gonna be represented in little endian method. Just we have to get that ingrained in our mind because when we can make like simple small errors when we do that, when we forget that it's being represented like that, or when it's being represented in hex, it can get really confusing. I totally get it. So let's run the program again. Let's give it a bunch of A's. Okay. It looks like I crashed the program because I caused a buffer overflow. And also, it looks like I overrided the address because before it was this and I overrided it. And if anybody knows what is hexadecimal 41 in ASCII, let's take a look. 41. So 41 is A. So what does it look like is happening with our program? So I gave it a bunch of A's and it overrid the address. So it looks like it's taking our whatever input we give it and it's overriding it to that address. So it looks like we might have to figure out where the flag is so that we can override it to the address of the flag so that we can manipulate the message and override it so that our address becomes the address where the flag is, so it can print out the flag file for us. So we can do that using GDP. So I'm just going to, so now we've entered GDP. It's perfect that PicoCTF comes with it. So what I'm going to do is I'm going to do a command called info functions, which is going to give me the address of where all the functions are and some more information. So here's all of the functions taking place. Anybody see a function that should be of particular interest to me? Anyone see flag? Flag is probably where my flag is. Correct. Yep. So flag is probably where my flag is. So now that I know where this is, does anyone know what I would have to, like, what should be my next step? I know where the flag is located. It's at this hexadecimal address. What can I do to print the flag? Because this is not a shellcode program. We don't have the option to, put in a shellcode and get it. This time we have to find another way to print the flag. So does anybody know what I can do that will allow me to print this flag? Let's get out of this program by Control Z. So we know that the flag is right at this hexadecimal value right here. We also know that right over here, that when we gave the program an input, this string, we were able to override with all the A's. So we just have to figure out how we can manipulate it so that we can make the address the same as the flag address so that we can get the flag. So now let's try to get our program to come at that location, okay? So let's run the program and maybe let's try giving it that flag value, right? Let's give it that flag value and it's in hex and we have to give it with little endian methods. So that's going to be E6, XE6 because it's in hex, X85, X04, X08. Let me just make sure that it's correct. Yep. Okay. Okay, so that didn't really do anything. It's still the same. So that means we haven't overridden it enough. We are still there. And it might be taking this as a string. It's expecting a string input. So maybe it's taking it as a string. So let's print this. And let's print X86, X85, X04, X08. And let's put that in the brackets. Oops, let's put that here. Let's put that all in a bracket. And let's pipe it into the program and let's see what happens. I didn't put the slash, so it didn't run. Okay, so nothing happened. It didn't override it. So let's see. Maybe we need to add some A's. Times 50 plus. Nope, didn't work. Let's try 100 A's. Okay, so we were able to override it, but by giving it 100 A's, but we overrid it too much because it didn't even consider looking at what was after. So let's try. So I know it's between 50 and 100. Does anyone have any idea of what number I could try next? Does anybody have any suggestions? 75. Okay. Okay, it looks like something is happening. It looks like that the address is changing. So let me just see if I have made an error in my code. It's not giving me the output that I expect. Oh, that looks right. That looks right. Okay, so let's try 75. As you guys saw, if we did a lot of trial and error, we would obviously do 76 after trial and error, and you guys saw the solution. Okay, so there's something wrong with my code because let me see if I put it properly. It's not giving me the output that I expect. It might be the way that I wrote it. Just copy and paste it from here. Just save us all time. Let's see what I did wrong in the code. Print right here, right here. Oh, yeah, no, the double quotes are right here. So I have no idea why it's not. Let's see. That looks pretty similar. It might just be the addition sign, forward. Oh, ha ha ha. Yes, the slash is the wrong way. So let's see. Okay, so with 76 A's and the right syntax with putting the slashes the right way, we are able to jump to that address. And when we are able to jump to that address, that's where our flag is located. And this is our flag right over here. So that was easy, right? So let's try that again. So what we exactly did was, how we would have figured that out is we could have done trial and error. We could have looked at the buffer size. So if we had like 100 A's, again, we see that it completely overrides it. So that means it's too much. Then again, if we give it 75 A's, it should have shown us that some of the address is getting over. We're able to write some of it, right? So we see our 8 is almost here. We see the 04 and we see the 85. So it looks like we just need one more byte. So we could have done it like that. We would have, as we got closer, we would have seen like parts of the address getting manipulated, and we would have been able to get to that address. And that was made possible through GDB because it allowed us to see exactly where the flag function is located. So that was really helpful, right? So that was the solution, trial and error to see how many characters are needed to override the jump address to the address that we provided. You could have also, before putting in the hex value, seen how many A's were exactly needed, and then after knowing how many A's were needed, input the code, but it's however you want to solve it, whatever you're comfortable with. But you've seen multiple times today that small little errors like not having your slashes the right way, or not, having the quotes in the right place, missing a quote, which is very common when programming. It doesn't allow it to function properly. So to make sure that you're always checking your code and always having a second pair of eyes look at it helps. Like you guys were able to help me fix some of my code today. Now let's talk about mitigation against buffer overflow attacks. We saw that like secure coding is very important, that none of those programs were boundary checking. They had buffer sizes of certain values, but there was nothing that was being done to actually check if that value was actually what the program was expecting, and it allowed it to override that, causing a buffer overflow. So it's really important to have secure code that does boundary checking and input validation. There's what's known as a canary, which can also be looked at as a hash, kind of. And if that value matches, we're going to be talking about stack canaries next in 201, but that's a way to mitigate against buffer overflows. And then you can mark areas of memory as no execution or execute disable. Some of the Intel processors, the terminology they use is XD. So when you mark those areas of memory as NX or XD, the processor will not execute any code that's residing in those areas. So that is a way to mitigate against buffer overflows. Also, you can have rules set up in your intrusion detection systems and your intrusion prevention systems and your firewalls. It's important to have logging set up to see if someone is inputting weird stuff into your programs, to be able to prevent them before they're able to cause memory corruption or buffer overflow attacks. So again, buffer overflows are one of the most common types of attacks that take place. They're a nightmare for cybersecurity individuals because it's hard to prevent against them, because you have to make sure that every program is secure, right? So it's important that developers start coding practices that are secure, and that we're aware of what's really happening in the program, and we're debugging to see if there's a vulnerability that can be exploited as cybersecurity professionals. Yeah, someone mentioned shadow stacks that prevent stack overwriting, return addresses. Thank you, Adrian. That is a great way to mitigate against buffer overflow attacks as well. These are just some ways. There are many ways to mitigate against buffer overflow attacks. So here are some of the resources. I will now go ahead and copy and paste them, but the slides will be available, so you will have these resources later if you're not able to get them now. Let's see where the chat is. So that brings us to the end of the presentation of the workshop. Thank you guys for joining us. We are here for any questions that you guys might have. Albert and myself are here for any questions that you have. Just a reminder that the RVC Mentor workshop has been postponed. We'll let you know when it's going to be. And by the end of next week, the 2021 workshop schedule and office hour schedule will be shared. It will also be up on the CanHack resource hub. So stay tuned for that. There will be a workshop next week on intro to critical thinking. It will be an hour long, and it's going to be very exciting. It's going to be with SANS Institute, which if many of you are not aware, SANS Institute is a leading institute for cybersecurity. They certify cybersecurity professionals all around the world. So it's going to be a really great workshop. So please make sure to attend. And that's all for this. Thank you for all of you who've tuned into all the workshops throughout the semester. And I really look forward to the workshops in the second semester. Make sure that before you join those workshops, you watch the 101 workshop, because they will have a lot of preliminary information that's important. And we're here for any questions if you guys have. But thank you guys once again. Enjoy your holidays. Have a great time, and have fun with these challenges, and don't give up and don't get discouraged, because they are pretty challenging. Thank you guys. We're here for any questions. Yeah, these last two workshops have been on the more challenging side. And there are some resources that I shared, so make sure to check those resources out, because there's a lot of helpful information in them. For these two workshops, for anyone struggling, I really recommend that you go through you try to really understand what's happening in memory and stack, because that will and assembly language, because that will really help you to understand what's really happening. Without the strong background knowledge in that and also in scripting, it might be hard to understand, but make sure you don't give up and that you keep trying. Yeah, the 2019 competition is online. It's available on the Pico CTF website, 2019game.picoctf.com, and it's also available on picoctf.com. With the 2019 game, you can directly access the shell server where all the problems are located. If you go into the regular PicoCTF, the challenges are there, but you don't have access to the shell server within. So you might have to SSH if you're going to use that platform. So thank you guys for joining us. We will all see you. I will see you in the new year, because this is going to be the last workshop that I'm teaching for this year. And then we're going to start off next year with all the 201 workshops.